Basins, case studies, and here we are in the Alberta Basin, the Rocky Mountains right here. That's the major thrust, Rocky Mountain thrust. Some of you may have gone to Calgary and driven towards Banff, Lake Louise, and you see this very impressive frontal thrusting, very old sediments, Devonian sediments on top of Cretaceous sediments. And so this is the basin here. This is a so-called, and we're making things slightly complicated here, it's a retroarc foreland basin. It actually was an island arc at one time, and it was a back arc basin, and then due to the collision, it actually developed into a foreland basin. So if you look at a cross-section here, there's, well, what we see here are actually oil and gas fields in black. It's very, very rich oil province. Right here, this is the Canadian Shield, the Hudson Shield, and what you see is originally the sediment into this basin here was shed from the Hudson Craton into this back arc basin, and when it developed into a foreland basin, then the position, actually the sediment source, came from the Rocky Mountains, the nascent Rocky Mountains at the time. Big areas here. So this is actually this is Alberta, right here, and this is Saskatchewan, and that's British Columbia. Thank you. All right, so cross-section across here, we see the Craton here. We see the basin infill. You see here, these are the back arc basin when there was actually an ocean here. There was an island arc, volcanism, and then finally this whole terrain to the west actually came to lie on top of this whole thing and of the back arc basin, and then the sediments were shed from the Rocky Mountains into this foreland basin here, and they're still being shed. And so this is a big province. What's interesting to know is that up here, right up here in this area, we have the famous tar sands, Alberta Athabascan tar sands, and if you look at them at the cross-section, they're somewhere here, in here. They've migrated all the way up from quite low here, well, the oil, not the sand, has migrated ways up from down here, some carbonates actually. They've temporarily were stored in a place called the Leduc Trend, and then it continued migrating to the surface, and when it reached the surface, it got degraded, biodegraded, and became heavy oil. So that's sort of the inverse of what happens in maturation when heavy oil gets lighter and lighter due to cracking. And when it gets to the surface again, it gets oxidized, it gets biodegraded by bacteria and so forth. And so much oil that's been found at the surface, such as in the Orinoco Belt as well, is very heavy. Case study, California. Right, we have here a case where we said we have a strike-slip fault, a San Andreas fault here. That's the Pacific plate right here. That's the North American plate, but in fact it's a much more complicated story. There's many different subplates in here, and the North American plate really only starts truly east of the Rocky Mountains. So what we have here are back arc basins, strike-slip basins, pull-apart basins. Here's the San Joaquin Valley, right here. There's go up to Sacramento, but it's basically one basin here, and that's related to the strike-slip movement along here, and to the back arc situation that we find here. So it is a combination basin. You see in here, in between these faults, you see true pull-apart basins right here, very small ones, right here and in here. Yeah, down in Los Angeles, right here. See, the situation is very complicated. This the San Andreas Fault actually branches off here and follows here. This is an area called the Cajon Pass. It's very complicated, seismically extremely complicated, and many small subbasins. Now, of course, Los Angeles itself is actually, I showed you the tar pits, the La Brea tar pits, but there's actually other big oil fields in this area here, and that is actually the first time where offshore drilling and deviated drilling has been tried, because they knew onshore there were oil fields, and then they slowly said, well, if it's onshore, it must also be offshore, and they started drilling deviated holes from an area called Long Beach, and they drilled offshore, deviated wells, and then finally they actually moved the rigs offshore on barges and started offshore drilling. So that's the first place where that happened, and that's this oil province shown right here. And here you see the reserves. These are ultimate recovery in billion barrels, and you see that the San Joaquin Valley here, this part here, is by far the richest around Bakersfield, and down here Los Angeles is also big. So there's quite a bit of oil in this area here. All right, let's go to the real big ones. Middle East. So when we talk about the Middle East, we talk mostly about the Persian Gulf and surrounding countries. So Iran, Iraq, Kuwait, Saudi, this is the island of Bahrain, Qatar, and then to the east are the United Arab Emirates. Those are the main countries that we're looking at here. So why is this such a rich oil province? Do we see mountains? Yes, we do see mountains, the Zagros Mountains right here. But that's a collision. That's a collision between Eurasia up here and Africa, Arabia. They belong together, right? So that's a major collision zone, and the Zagros thrust, which runs right through the city of Shiraz and causes a lot of earthquakes, such as the one in Bam that we had a few years ago, very, very destructive earthquakes. I myself was working 2 years in a city called Ahvaz here, and it was quite normal to have an earthquake, sometimes at night or so, to be woken up, and then you just go to sleep again if nothing really bad happens. And so this is seismically very active, okay? And this is not, of course. That's a stable continent. So if you look at this whole area where the oil fields are, so this is split up into two maps here, then we see here Iraq. Let's go back here. So that's this bit here, right up here. We see Iraq. This is the Gulf here. Well, it's not shown here, but that's Iran, Iraq, and then the border to Syria and Turkey. North is actually towards the upper right here. And this is the famous Kirkuk field right here. And you see lots of other fields. You go into Turkey, it continues right there. There's a few fields around the Kurdish city of Diyarbakir and a little further inland as well. They're all on a trend. And if we look at the rest around the Persian Gulf, you're not allowed to say Arabian Gulf, by the way. Then we see the fields in Iran. They're actually down here. This is the where it continues, right? They show the same trend, very big ones. I showed you, no, I didn't show you, but I will show you a cross-section through here. And then you see down here along the coast, very, very big oil fields. We see up here around the city of Basra, we see very big oil fields. We see oil fields around here in Kuwait, the famous Burgan oil field. We move down here. We have some offshore fields, very big offshore fields here. This is the biggest one. That's the real big one. Does anybody know the name of this field? Biggest oil field by far. It's called Al Ghabar oil field. Huge. Got hundreds of billion barrels of oil in place. And then we move down here. Bahrain sits on an oil field. The Dukhan anticline in Qatar was one of the earliest oil fields to be discovered. Here, this is the northern field, which is shared between Iran and Qatar. It's the biggest gas field there is, by far. It's about 10 times bigger than the Groningen gas field. We go into the Emirates here, very big onshore and offshore fields. And then finally down here is Oman, and it also has its share of oil fields, although these are very small. And we know, of course, that the biggest reserves are right here in Saudi Arabia, in Iraq, and in Iran. And as far as the production is concerned, the Emirates have actually the best ratio because they have relatively low production, but very high reserves. Now, the question is, of course, now, how come these oil fields are here? So do you see any signs of what would give you an idea of what the origin of these structures is? So you have to look at the alignment here. For example, these look very different from these, right? The southern Emirate oil fields. They're sort of roundish on the right-hand side, right lower side, and on the right-hand upper side, the Iran and Iraqi oil fields, they seem to be elongate. How could that be explained? Hello? Are we in the same class here? Yeah? Yes. So you say these are related to the basins. Now let's just go back to the structures here, right? It's probably a little difficult to see, but these are very elongate folds right here. Very nice. The Zagros Mountains, it's a mountain range that goes actually very high. Some of these mountains have actually snow. They're snow-capped the year round. Well, these are folds. These are folds on the southwestern bit of the Zagros Mountains, and it goes all the way into Iraq on the left slide here and into Turkey. They're all elongated along these long anticlines. And now that these down here, they're more roundish. You know, you're far away from the mountain range here. You have this 4 deep here, the Persian Gulf, right, the shallow sea. And these are more roundish here. So what could the origin of these be? Well, these are actually, many of them are actually based on salt domes. They're carbonates that have grown on salt domes. So you have reefal structures that build on salt. Whenever you see round structures, round oil fields, you know, something has come up to form that round structure. And here it's salt, including this structure here. And if you look at the Gawar field, that has again a different structure, a different alignment. It's not along the alignment of the Zagros folds. It's not round. It has actually a completely, pretty much north-south elongation, and it actually splits up. And there's a few other fields around it that have the same orientation, such as number 73 here, and also the Qatar arc and the Bahrain arc here, and a continuation offshore of the Gawar field right here. Well, that's difficult to figure out, of course, just from the information I give you. These are very big basement horst blocks. So the basement actually has moved there and has formed a very gentle uplift. And that has actually a closure here of almost 100 kilometers in length, or I think it's even more if you look at the scale down here, and a width of about 30 or 40 kilometers. It's a huge structure, huge structure. And if we look at a cross-section, this is really just a set of slides, a set of vertical columns, stratigraphic columns in the Emirates. This is in the Emirates, as you see on the map on the lower right. And what you see here is in green are dolomites, in blue are limestones, in brown are shales, and in pink are anhydrites and salts, what we call evaporites. So what you see, the whole sequence here is completely dominated by carbonates and evaporites. There's did you hear me say sandstone? No, you didn't, right? Because there's no sandstones here, or practically no sandstone. There actually are some, but very thin ones, right? See, sandstone's actually light brown or yellowish, but we don't see any here. This is a carbonate province, and has been a carbonate province for pretty much most of the more recent geological time. Here we talk about the Permian, here is the Triassic on the left side, right? So ever since the Triassic and the Permian, in fact, you know, this area has been dominated by carbonate deposition. Yeah, I showed you when we talked about carbonates, I showed you a slide, an aerial view of the area, you know, where you saw different types of carbonates being deposited. Well, that's the result. Some of it is dolomite, some of it is limestone. We have a shale, and we have some anhydrites. And what are the shales good for? Well, they're the source rocks. Thank you very much, Mother Nature. And what are the salts and anhydrides here? Well, they're the seals. You see, the Gabar oil field is actually at this level here. That's the seal, the Hith anhydrite, right here. And these are the Arab, very famous Arab formations right below, which are mostly limestones, and they are just enormously thick, right? And that's sourced from down here, from shales down here, has been sourcing this very, very thick carbonate here, which is capped by this completely impermeable Hith anhydrite. So you have a combination of very porous carbonates, good source rocks, very good seals, and very large structures, and practically no faulting. Remember, faults are generally not our friends. They can be, but it's usually not a good thing, right? It can be if they're really capped, if they terminate, but if the faults go through typically all the way to the surface, then that is typically not a very good thing to have. So they don't have that. It's very, very little faulting, very gentle structures, large-scale structures here. And what we do here, we make a jump back to about 80 million years in the Cenomanian. And this is a reconstruction by Mr. Roel Murris, who was a geologist with Shell. And he reconstructed the situation at the time of the early Cenomanian. What you see here in colors are the different kind of deposits that were formed then. You see here in gray the outline of the present-day Persian Gulf. The Strait of Hormuz, where all the tankers have to pass, right? And then Oman down here, the lower right. What do you see? Well, in blue you see the carbonates, and in pink carbonates and evaporites, and in greenish mixed clastic and carbonates. And all of this is dominated, this area that covers the present-day Persian Gulf and ways up to the north, is covered by this shallow sea in which actually carbonates are deposited. And here on land we see sand, alluvial plain, lower coastal plain in yellow and brown. Well, that's exactly the situation we have now. You see, the Saudi desert is sand, right? But the Persian Gulf is carbonates, except here this sea was much wider than it is now. Well, that has to do with the collision of Arabia with Eurasia, of course. So that sea got shortened a little bit, right? And it went ways up into Turkey, Iraq and Turkey, and that is all filled now with clastic sediment. So that's no longer a sea today, but this down here still is a sea. So it's kind of a remnant of an older sea that was much bigger and that was equally carbonate-rich as the present-day Persian Gulf is. That, in a nutshell, together with this very large-scale structure, that's the secret of the Middle East. It's basically geological stability. You know, that doesn't always go with political stability, but in this case, the geological stability is essentially one huge sequence of shallow water carbonates and evaporites, ever so often interrupted by shale deposition, which was very useful because that actually produced the source rocks. Okay, so we have just a few more things to say. We've looked at the basins now. I showed you some of the really large-scale basins, important petroleum basins in this world. And what I'll show you now is how we go about exploration and production. So in other words, how do we actually find this and how do we drill for it? Then finally, how we calculate how much oil there is in it. Now that'll be very short because that's not really the main focus of the course, but I think it's still useful to have an overview of this. So what we have here is a time axis, and here are different methods. This would be at the beginning of exploration, and then this at the right-hand side, we would go into production. So what do we do in the beginning? We make surveys. We make seismic surveys, gravity surveys, magnetic surveys. We look at surface geology and some remote sensing, such as satellite imagery, to see essentially what's the shape of the basin, are there any structures in the basin that might be promising, and so forth. All right, so the seismic is shown here actually at a later stage, But today, what we shoot very often at a very early stage is so-called spec seismic, speculation seismic. And that's usually done by contractors that do that on their own without having a contract, and they basically shoot lines. Yes? Yes, I'll get to that. So once you've identified, so the question is, isn't there any drilling at this stage? Well, this is the very early stage in exploration. You see, for example, that is the stage where the Arctic basin is in, right? There is hardly any drilling there, in Greenland as well, and some other very, difficult basins, such as the Tarim Basin, very, very little drilling, but a lot of surveying. So this is surveying. But your question is, okay, when do we actually drill? Well, as soon as people think you have the right combination of factors, and we all know what they are in the meantime, some company might be willing to put down some money, invest into an exploration well. So that's what would be this, right? So you shoot seismic, you zoom in. Typically today, that's all 3D seismic, and the 3D seismic lets you see the structure in much more detail than these remote sensing methods here, and that lets you actually place a well quite accurately on a promising structure. And that's when the first drilling takes place. That's right here, right? And then drilling might go through, appraisal drilling, and then finally they might say, all right, so now we're having production wells, and then of course you're cranking up production. Very simple. That's sort of the flow, the workflow in a very general way. So I'll go through these steps a little bit one by one. And we looked at the Middle East before. Now I show you here a satellite image from the Zagros Mountains. And you see these very long anticlines right here. You see them one by one. They're very high mountains. Some of them will go up to 4,000 meters. Right? And somewhere up here to the very top, above the very top of the picture, is the Zagros Thrust, the main collision between Eurasia and Arabia, or Arabian Africa. And we see these dark patches here, right? And we, of course, wonder what they are, right? And that's actually salt. That's pierced salt domes. The salt actually has pierced all the way to the surface. And some of it actually has developed into glaciers. See, for example, here the salt actually flows down the valley, right? Or here, it flows actually down into this valley here, right? You probably never heard of salt glaciers, but they're a fact, right? Here. Now, why is it black? Well, because that's surface weathering, right? What you see at the surface is not the salt. That's the residue, because the salt at the surface weathers, dissolves, and what remains is whatever is left over once the salt is dissolved. And that's residue, whatever was in the salt, and that's typically colored black. And so the salt is actually below, but it flows, right? It still moves. All right, so, but this region here, this is towards Baluchistan, towards the Pakistani border. There's no oil fields here. There are oil fields, they are actually to the northwest of here, where there's no salt piercements. The structures are a little more gentle, but still this area here is very promising, but it's completely underexplored, in fact. And there are a few exploration wells that were drilled. It's still one of the most promising areas here. But with satellite imagery, you can actually see very accurately where these structures are and where you have faults. And faults typically would mean that the anticlines are breached and therefore oil has escaped. And where there are salt domes, and that probably wouldn't be very good news either as far as trapping is concerned. All right, gravimetry. This is southern England here. Gravimetry can actually be airborne or land-based. What you look at is anomalies. And why do you look at anomalies? Well, because if you have, for example, a salt dome, well, salt is lighter than the surrounding sediments. You would actually see an anomaly in the gravity, the so-called Bouguer anomalies. And I'm sure most of you have heard about that. And so by mapping things like that, obviously in England the structure is very well known. This is just by way of example that I show you this. But if you see structures like these here or these here, you might actually want to find a reason why we have such anomalies. And the same thing with magnetometry. This is the northern coast of Ireland right here. And this is a map of the magnetic anomalies. And again here, if you see structures like that, clearly aligned, alignments, you might wonder what that is. And for example, igneous rocks, they have different magnetizations than sedimentary rocks. Typically sedimentary rocks have very poor magnetizations, whereas some igneous rocks, and particularly basalts, have very strong magnetizations. And so that would actually indicate a certain structure. Well, what kind of structure? Well, obviously only gets here a picture of the large-scale tectonic units. But by modeling, in fact, for example, here we have so-called half-graben intercratonic basement. As you see here, it basically has only one fault. It doesn't have two faults. If it had two faults, it actually would rift, would become a rift, perhaps. And so it has only one fault, so it's a very asymmetric basin. You see the basement rocks below. Now, these are relatively lighter rocks than the surrounding basement. And so if you look at the anomaly, the gravity anomaly and the magnetic anomaly, they both would actually, the gravities would decrease and the magnetizations would decrease as you go to the parts of the basin where the sediment thicknesses are greater. And then that would jump up again, right? Or you could look at the basement faults, such as here, quite similar to the situation right here, just inverted. The situation in A, in B, they're quite similar. And here in C, we have a reef. So a carbonate buildup, and that might actually be a little heavier than the surrounding shales, and so you would see on the gravity, you would actually see an anomaly, whereas on the magnetization, you wouldn't really see anything because both are sediments and they're relatively poorly magnetized. And so forth. Here we have a basaltic, in D, we have a basaltic intrusion, and that is a highly magnetized rock, and so we would see an anomaly on the magnetization, but not necessarily on the gravity. And in the salt dome, we have just pretty much the inverse, as shown in picture E here. The gravity would strongly decrease above a salt dome, but the magnetization, since all of these are poorly magnetized, would actually have perhaps only a minor dip. Okay, and so what you really measure this here, perhaps in 2D, and you can actually use that to make a model. You make a subsurface model because you know a little bit what the geologic context is, and so you can actually assume a certain structure, and you can see whether by forward modeling you actually can reproduce the actual measurement. And so it is sort of an iterative forward modeling that is being used. You're sort of stacking layers. You're assuming, well, it could be that we have a salt dome here, so let me put a salt dome here. You make a model, maybe just a 2D model, not a 3D model. You fill them with properties, magnetic properties and densities, and then you're calculating the response you would see at the surface in terms of gravity and magnetic anomalies. And then you vary the parameters, the densities and the thicknesses and so forth until you find a match. That's not unique necessarily. That's not a unique solution. You might have several situations that actually might give you the same response. And so these type of surveys, they're still being used. They're actually being used quite often by Russians, and they made big discoveries that way. They discovered the Tengiz field. It's the biggest field currently in Kazakhstan. They discovered that with gravity anomalies. They discovered the White Tiger field offshore Vietnam, the biggest field in Vietnam, also with gravity anomalies, which is a granite basement horse block. And so, don't discard these kind of things. They are important. I know most of you are interested more in seismic, and it is true that seismic is more often used. Here it is. This is actually a cross-section right north of here, through an oil field called the Moore-Capella field, which is a fairly big field, in fact, but it contains heavy oil. Now, does anybody see a structure here? You say a fault, but a fault is not a structure. A fault is just a fault, yeah. Hmm? A reef? Where do you see a reef? Here? Maybe? Yeah. Yeah. Any other structures you see? Excuse me? An unconformity? Yes, there's a big unconformity right here, huh? Right. That's the Cretaceous Tertiary unconformity. Very common here in the southern North Sea. Yeah, but that's not a structure by itself. That wouldn't be a trap. Right, so it's a complicated story here. Right, and it's difficult to see. Well, the oil field is actually in here. Right, in the right middle part of the structure. And we see on the left side, we see faults. On the right side, we see faults. 2 or 3 major faults. And overall, the layers are actually dipping towards the right. And that's why we have this angular unconformity right above here at about 700 milliseconds two-way travel time. And what this is, it's an inverted structure. And this is actually, this part of the world here was actually a fairly deep basin in the Cretaceous. Lots of sand got deposited. There was actually a high to the south of here, just the London Brabant High, and lots of sediments got shed into this basin here until it was filled. And then a very important tectonic event took place in Europe. Which was that? There are Swiss guys here, I should know, okay? What's the dominant feature in Switzerland? The Alps. And how did the Alps come into being? Well, that's a collision of Europe and Africa, right? That's a strong compressional event, and it didn't go unnoticed here. You see this structure here, that's the subsurface mountains we have in the Netherlands. We don't have them at the surface, right? We have them in the subsurface. So that's the collision, that's a result of a collision of Africa and Europe. It's right there, right there. And it's an inverted structure, so what was originally a basin got uplifted. So what was low became high. That's called an inversion, a structural inversion. Yeah? So these sands in here, these are actually fault-bounded traps in here. They are sourced by sediments fairly deep down at about 2 seconds to a travel time. That actually got migrated up along the faults into these structures. Here, sort of looks like a pyramid, and in the center of that pyramid is the Moerkapelle field. It has actually in excess of 100 million barrels of oil, but very heavy oil. Now, you all will take courses in seismic interpretation, and there's lots of pitfalls. I put them together here that, you can actually see structures that are not structures. Like, for example, here, you have in the middle, you have actually on the right-hand side, you see the true situation, which is a salt dome, and because salt is relatively slow, you see underneath very often an apparent pull-up. Then you say, oh, we got a structure below the salt dome, right? No structure below the salt dome. It's an apparent anticline, right? It has to do with the velocities, the relative velocities, compressional velocities in these structures. And there are other examples here. But most of you will take courses on seismic interpretation, or you already are taking courses, so I'm not going into this. The most important tool we have today is seismic stratigraphy, as shown on this slide here. Again, I won't go into details, but we've seen in the Gabon case, the West Africa coast, we've seen how these coastlines prograde. They move out, and of course they don't do that continuously. They do that actually in bits and pieces, and sometimes the sea level rises, and then the whole coastline gets shifted again back, and then it drops, then the whole coastline gets shifted forward again. I showed you a simulation of that, right? And the end result of that is a very complex build-up of the coast, the coastal sedimentation, as shown here in step 4, the lowermost picture here, where you see the different bits that actually belong to such a coastal buildup, you know, forming rather intricate structures that you have to understand. Once you understand that thoroughly, you can also pinpoint potential traps, as shown here by these base of fans, slope fans, and the platform carbonates, reefal buildups, and so forth. These are all possible places where hydrocarbons can get trapped. So that's why it's really quite important. And so the common thing is to these coastline progradations, generally if they are not in a collisional situation on a so-called passive margin or a passive basin margin, then very often the depot center migrates, as shown here, and we've seen that very nicely in the case of the Niger Delta, that you see here D1, D2, D3, right? And these are, you know, stratigraphic thicknesses, which are the maximum thicknesses for each one of these time wedges. The black lines are time lines, right? So the last one is actually present, right? And as you go towards the right, these timelines become older and older. And so if you're taking all these thicknesses, you add up D1, D2, D3, you might think, well, this is the total sedimentary thickness I have. No, it's not, because the depot center has shifted. From D1, it has shifted to D2 to D3. But you saw that already in the Niger Delta, I guess, and it's very important to keep that in mind. How do we evaluate a prospect? Well, we all know the factors that play a role. We need a source rock, we need a reservoir, we need a trap, we need a seal, and we need the right maturation. And so geologists, they usually don't like complicated mathematics. Normally they can multiply, and that's good enough to evaluate prospects. What you do is, here are 4 different prospects, and what's shown is the probabilities for each one of these criteria. For A, the probability of source is 0.9, the reservoir is known, it's 1, the trap, 0.7, good seismic, they see a trap. Probability of a seal is 0.8. They don't see a fault, but they're not quite sure if maybe there is a subseismic fault. And probability of the maturation level is 0.6. And what you do is you calculate the combined probability by multiplying these 5 numbers here, and you get a combined probability of 0.302. All right. And so if you go to the other examples, B, C, and D, you see that each one of them has at least one of these criteria that's quite low, such as the maturation level in B and C. And in D, the probability of a seal is 0, so obviously this is not a prospect. There's no seal. So the oil has, if there was ever any oil, you know, it has actually leaked out. So only if the combined probability is relatively high is it worthwhile to drill an exploration well. That's how you do it. Here's a rig, right? A platform. Does anybody know what kind of platform this is? See, this is the sea, the sealer. Yeah, it has a slightly different name, not submersible, semi-submersible, because only half is actually submerged. So these are actually pontoons here. They're air-filled, and what you see down here are they're propellers that actually hold it in the right place, and they're all GIS monitored. Sometimes they're tethered. There's at the seafloor, there are reference beacons, and so these things are dynamically positioned at the right place. And that's where the drilling takes place. You usually have a few slots where you can drill, typically like 8 or 16 slots. So you can, from one of these guys, you can actually drill 16 different wells, all in different directions. You drill a well through the reservoir, but you think is the reservoir right here, where you think, well, this is where the oil must be, according to my probability calculations. Up here above it is the rock. You drill a hole, you set casing. Casing is an iron pipe, a tube that you put in. You cement behind the casing, so this is tight. It's completely tight. Then you set tubing. That's this inner tube right here in the middle, with a packer to isolate the tubing from the casing. and then you're perforating the casing and the cement in the reservoir to make the oil flow out through the tubing to the top, and there's a thing called a Christmas tree, which is essentially an arrangement of valves, and from there it goes to a separator where you separate the water from the oil. So that's a quick and dirty course on production technology. How do we calculate reserves? And what are resources? This is, on the vertical, we see the economic feasibility of extraction, and on the horizontal axis, the decreasing knowledge. If we are in a case where we know something's there, could be there, but I don't really know, and it would be very expensive to produce it, we call that a resource. And if we go to the very left lower end, where we know that it's economic feasible and we know exactly what the geology is, that we call that reserves. And we actually have to provide the calculations of reserves to an authority called the STC. They're based in the US, and they actually have to approve that. And then you can book reserves. You see, reserves are like money in the bank, right? And if you have shareholders in your company, they want to know how much money the company has in the bank. And so that's a very important exercise to go through. And so you see this second solid line, approved reserves. That is the most important information an oil company provides at the end of the year. It's not so much how much they have produced and the net income, but how much reserves they have. And so this is a same graph, or the same idea in a different graph, I should say. And what you see here are a horizontal line in the middle, that is the splits the sub-economic from the economic bit. And what is above the economic line, this horizontal line, is all called reserves. You can actually produce them, but you have different degrees of probabilities of those to be present. Everything's about uncertainties and probabilities in a subsurface, because you can't go there directly and measure it physically. So it's always a matter of calculation, probability. So you have proved reserves, you know they are there, because you have drilled wells and you found that all in this area there is oil, and it certainly can be produced. Some of it has been produced, and some of it is undeveloped. And then you have a whole area, a whole box that's called probable reserves here, that is probably there, but you're not quite sure. And you have another box called possible reserves that might be there, but you're even less sure than for the probable reserves. So that's the reserves, and what's below the horizontal line in the middle, that's the sub-economic bit. It's there, but it's too expensive to produce, and that's the resources. And some people call the whole thing resources, reserves and resources, as shown here, and some people only call resources what's below this horizontal line. So these are different probability curves. I won't go into detail, because this takes whole lecture actually to do that. But what we see here again are the possible, the proved, the possible, and the probable reserves. And if you sum that up, then that actually gives you the total probability curve, a cumulative probability curve, shown here from 0 to 100%. And you have a mean somewhere, so that's what you expect it to be. You have a minimum and you have a maximum. In fact, this graph is rather complicated because it needs a little bit more explanation. This actually, the summation is actually not the summation of the three curves that you see on the left. So reserves, they can take very interesting shapes, such as shown here, oil reserves in an OC, which somehow seem to fall on a log normal distribution. You see this is log plot. Here is just a logarithmic one, and this is a log normal graph on the horizontal, and then somehow these points fall in there. Nobody's really has a good explanation for that, but that really is a bell curve. If you plot that on a linear scale, that would actually mean that the reserves are sort of a bell curve, Gaussian distribution. And finally, reserves by basins. These are not perhaps the latest numbers here, but you see here the large basins, Arabian, Iranian region has by far the most reserves. This is in billions of oil equivalent. And so, you know, you see that it's dominating by far. Just before, second would be the West Siberian Basin, Volga-Ural Basin, some basins that you may not have heard of, the Maracaibo Basin in Venezuela, Mississippi Delta, and so forth, in decreasing order. And you're winding up with the reserves shown here below. These are numbers from about 2000, and they've changed a little bit. It doesn't really matter, you know, they're updated sometimes. But just to give you an idea, the world oil consumption, and I showed that in the first lecture, is 30 billion barrels of oil per year. The Kashgan discovery, recent discovery, big discovery in Kazakhstan is 70 billion barrels. So that's good for about 2 years' consumption. A giant oil field, as Kashgan, is good for 2 years' consumption. And the average deepwater discoveries in Angola are 2 billion barrels of oil. So that's good for about 4 weeks' global consumption. We're using a lot of oil, you know. Okay. Thank you very much. If you have questions, you can email me. I won't be here for the exam. A PhD student of mine will actually be there. But you can contact me by email if you have any questions. Okay? Thank you very much.